Hi, and welcome to Mike's Super Short Show, where we keep you informed about the latest Pchem research. Today we're going to talk about glutamine. Why glutamine? Because it plays a key role in understanding many neurodegenerative diseases, such as Huntington's disease. This is because of the presence of fibril-like structures containing polyglutamine segments in many of these diseases. Researchers at the University of Pittsburgh have actually begun to simulate the Raman spectra of glutamine in order to understand its structure further. Their research involves correlating the Chi2 angle on L-glutamine side chains to the frequencies of the CH stretch vibrations on the gamma carbon. Using DFT theorem and Pchem, they constructed a spectroscopic map containing quantitative relations between the Chi2 angle and the simulated frequencies of the CH stretching vibrations. The aim of this project is to eventually simulate a polyglutamine peptide. The more that is understood about the structure, the better the treatments that can be provided. So now you know, because it's my Super Short Show.
And that is why you get -1/12. Sorry for the mess. Concerning the mystery problem solver, my colleagues and I have confirmed, and there's an experiment out on the board outside right now. It's taken us over 2 years to find a method for this. Let it be known, the gauntlet has been thrown down, and the faculty has answered with vigor. Then you have the nerve to say we have to make wave function great again. Stupid. Hey, what are you doing?
Sorry.
What? You can't mess with other people's work!
Sorry.
Unbelievable. Oh my god. He suggested to use a method that uses 2 calculations. One that simulates glutamine in a vacuum, and then another that simulates the Raman spectra of glutamine with deuterated hydrogens on the gamma carbon. All the geometries should be optimized, and all the angles should be held constant except the Chi2 angle. It's going to change in 15-degree intervals. I'm using the B3LYP exchange correlation functional with the 631G star basis set. Now analyze the change in frequency in relation to the angle changes. Run the calculations.
Welcome to today's episode of Hi Abri. I'll be answering some questions that were posted to Piazza. First question says, "Hi Abri, I know you're working on simulating glutamine. Can you tell us your results?" Yes. So what we exactly did was that we looked at the dependence of the CH vibrations on the beta and gamma carbons in glutamine, which are part of the side chain. And the side chain, and then they define part of the Chi2 angle, and the Chi2 angle is more specifically the carbon, that's 4 carbons in the side chain. So what ended up happening was that when we did this, we saw that the effect of the Chi2 angle, which was changed at 15-degree intervals on these CH vibrations, and how they coupled with each other, meaning which ones were in phase with each other and out of phase with each other, and the frequencies that were yielded because of this, was that there was a sinusoidal relationship, strong correlation between this Chi2 angle and these CH vibrations frequencies. So what we did next was that since these calculations were done in a vacuum, we did deuterated in vacuum calculations, meaning we deuterated the hydrogens on the gamma carbon. And what happened was that when we did this was that we decreased increased mu, which in turn decreased the vibrational frequencies, and caused it really showed the same relationship but more separated out data. And this is caused because in a harmonic oscillator, you know that the frequency is going to equal to the square root of k over mu, and as we said before, again, mu was decreased, increasing the frequency. So the second question goes from Anonymous. Hi Abby, how does this research help with understanding Huntington's disease? So what we did here was that we looked at the structure, meaning the angles, and how it affected the Raman spectra of a single glutamine. So what we could hope to do was that on bigger levels, meaning the polypeptide level, we could see the Raman spectra. Once we can establish this relationship, we can look at the Raman spectra and be able to deduce a lot about what the structure of the certain polyglutamine tract is. And once we can better understand the structure of this polyglutamine tract, then we can find more targeted and effective treatments for diseases such as Huntington's disease. And that's about it. So thanks for listening to the segment, and have a very good night.
It's not that hard.
TV's weird.